So here's another example of a related rate problem. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment the rangefinder's elevation is 45 degrees, the angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? Okay, so let's go through the process again. First thing we want to do is draw a picture. And so if we think of a picture of what's going on here, let's see, we have a balloon. There's the balloon. And it said it's a level field, which is good. And then we get a nice right triangle right there. And so let's see here, this is 500 feet away. And the rangefinder is looking at the elevation. So if you imagine you're standing out here or looking out here, and you're thinking of the elevation from the ground up, that would probably mean this is theta. That's what we're looking at. Okay, and this is at 45 degrees. And it's increasing at 0.14 radians per minute. Okay, we already have a unit mismatch, and if you remember, I always said work in radians when you're working in calculus. You never really want to work in degrees, so let's get rid of this. 45 degrees, I think that's what, pi over 4 radians, so we'll put in pi over 4 for our angle. Okay, so there's all the information we're given. And we want to know how fast a balloon is rising at that moment. Okay, so we're looking at how fast this is going. So the next thing we need to do is we need to come up with an equation that relates all this information. Now, a lot of times when we have a right triangle, we've been using the Pythagorean theorem, x squared plus y squared equals r squared. But in this case, considering we have a lot of information based on this angle theta, it appears that we're probably going to want to use a trig ratio or a trig function rather than the Pythagorean theorem. So we have this value here, x, we know we want y, and we have theta. So let's think, what would relate x, y, and theta? Well, that theta, that's opposite, that's adjacent, so tangent appears to be the equation we want to use this time. So the tangent of theta is y over x. Okay, so let's go ahead and take the derivative of this. So the derivative of tangent. Now this is something that either you remember or you have to rederive. If you need to rederive it, go ahead and just go off to the side and do that real quick. Actually, let's just go ahead and do that. I'll take a separate, we'll do it right over here. Let's see, we'll create a different one. W equals the tangent of theta. Then W is the sine of theta over the cosine of theta. So W prime would be the bottom times the derivative of the top minus the top, oops, I'm going to run out of room, times the derivative of the bottom all over the bottom squared. So that means W prime is the cosine squared of theta plus the sine squared of theta over the cosine squared of theta. That goes to 1, so W prime is 1 over the cosine squared of theta, which is the secant squared of theta. Alright, so that wasn't too bad. So sometimes if you don't remember the derivative of some of these trig functions, especially when you're on a test, you're thinking, gosh, what is it? It's okay to just do a quick little derivation off to the side, and then we know our answer. So let's come back down here. We have the tangent of theta is y over x. So now let's go ahead and take the derivative of the tangent. So the derivative of the tangent is the secant squared, so we have the secant squared of theta. Now remember, we're taking this with respect to time. So you have the derivative of the tangent is secant squared, then you have to take the derivative of the inside, which is theta with respect to time. So we're going to have d theta dt. Okay. Over here we have a quotient rule. Well, we just did the quotient rule over here, so you've got the bottom, x times the derivative of the top. The derivative of y is just dy dt, minus the top, which is y, times the derivative of the bottom, which is dx dt, all over the bottom square. Okay. All right, so now let's see if we can get all of our information here. So we have, oh gosh, so let's start over here. X is 500. That's from here. Dx dt, let's do that next. Okay, so that's the rate that our x is changing. And, well, if you think about it, I mean, we're over here measuring this angle. The balloon is going straight up according to our problem. So that means dx dt is not changing, so it's actually 0. That'll make things a little bit easier. Let's see, y. Well, right now we do not have y. Okay, well, let's go ahead and find y. So let's see, y would be this. I'm going to do this up here. Well, we know that the tangent of theta is y over x. So that means the tangent of pi over 4 is y over 500. So y is 500 times the tangent of pi over 4. And the tangent of pi over 4 is just 1. So we would get 500. Easy enough. dy dt, that's what we're looking for. Okay, so we also need the secant of theta. And we need d theta dt. Let's put d theta dt first. D theta dt, that one we got 0.14 radians per minute. That was given in the problem. Now we need, theta is pi over 4, but we need the secant of theta. So let's figure out if we can figure out the secant of pi over 4. The secant of pi over 4. Well, we know secant's 1 over cosine, so this is going to be 1 over the cosine of pi over 4. And let's see, the cosine of pi over 4 is the square root of 2 over 2. We get 1 over the square root of 2 over 2, which is 2 over the square root of 2. We can't have that, so we're going to have 2 times the square root of 2 over 2, which is just the square root of 2. Alright, the secant of pi over 4 is the square root of 2. Okay, let's put everything into our equation over here. So we have the secant of pi over 4, so I'll write that out anyways. The secant of pi over 4 squared, d theta dt is 0.14 equals x, which is 500, dy dt, that's what we're looking for, minus y, which is 500, and then dx dt is just 0, so that'll go away, that's nice. And this is all going to be over 500 squared. Okay, so secant of pi over 4, we got that. That was the square root of 2. So we're going to have the square root of 2 squared times 0.14 equals 500 dy dt divided by 500 squared. And that's going to 0 over here. Okay, now the square root of 2 squared is just 2. So we have 2 times 0.14. Now one of these 500s cancel out, so we have dy dt all over 500. Alright, multiply each side by 500, and we're going to end up with dy dt equals 500 times 2 times 0.14. 500 times 2 is 1,000 times 0.14, and then 1,000 times 0.14, I'll move the decimal points 3 places, so we end up with dy dt is going to equal 140 feet per minute. And so that's our answer. So at that moment, this balloon is rising at 140 feet per minute. That's actually kind of an interesting problem. I mean, this one is neat because if you think about it, like if you were to imagine you're sending a rocket up into space, I mean, it's easy for someone on the ground to know the distance from where the rocket was lifting off and then be able to measure the angle and the rate that the angle is increasing. So if you know the distance where the rocket's going up from and the rate and the angle that it's increasing, then you can figure out what speed it is going.